Okay, so we're going to look at some general physics past paper questions that we've done as part of a test. So let's start with question 1. Underline the vectors in the following list of quantities. Density, no. Energy, no. Force, yes, force is. It has magnitude and direction. Mass, no. Velocity, yes. Volume, no. We've picked 2, so that's our 2 marks. A small metal ball is projected into the air with a velocity of 40 meters per second vertically upwards. The graph shows how the velocity changes with time until the ball reaches its maximum height at about 4.1 seconds. Okay, so use the graph to find the time at which the ball reaches its maximum height. So, when it reaches its maximum height, its velocity will be 0, because then its velocity would become negative as it came back down again. So we can clearly see it's at maximum height around about 4.1 seconds. Okay, so we want the deceleration of the ball. So deceleration is the gradient of this graph. So what I'm going to do is pick essentially 2 points. I'm going to use the whole line here. So the velocity change from 40 to 0 and the time that passes is 4.1 seconds. That gives us an acceleration of minus 9.8 meters per second, or a deceleration of 9.8 meters per second squared. Okay, so we want the maximum height reached by the ball. So essentially we want is the distance traveled, which is the area under the graph. So that's what we're going to do. We want the area of this triangle. We know it's going to be half the base times the height, which is going to be about 82 meters. Okay. So add a line to the graph to show how the velocity of the ball changes after it reaches its maximum height. Your line should extend to a time of 6 seconds. Okay, so it's going to be like this. So it's still being acted on only by its weight force. So it should have exactly the same acceleration as before, which means the gradient should be the same. So we're just going to have a straight line continuing on from 4.1 seconds all the way up to 6 seconds. Okay, so a meter rule balances when the 50 centimeter mark is directly above a pivot, because the center of mass is directly above the pivot. State where in the rule its center of mass is located. So if it balances, the center of mass has to be exactly on or above or below the pivot. As long as it's on the same vertical line as the pivot, that will balance. So the diagram shows an apple and a 0.40 Newton weight placed on the rule so that the rule remains balanced at the 50 centimeter mark. And we've got some distances that they're placed at. Okay, so we've got the apple is 25 centimeters from the pivot and the weight is 45 centimeters. Okay. Calculate the weight of the apple. So I'm going to apply the fact that the moment clockwise equals the moment anti-clockwise if it's balanced or in equilibrium as we actually describe it. So we can say the moment of the weight force of the mass that we've put on there, we can do force times perpendicular distance, must be equal to the weight of the apple times its perpendicular distance. And we can rearrange that to find the weight 0.70 newtons. If we then want the mass of the apple, we're going to divide that by the gravitational field strength here on Earth, 10, and that gives us a mass of 0.072 kilograms, or 72 grams if you like. Okay, the apple is not moved, the weight is removed from the rule, and the pivot is moved to the left until the rule balances as shown. Okay, explain why the arrangement in the diagram balances. So the key is the weight force of the ruler itself now provides the clockwise moment. So the moment clockwise, the moment of the weight force of the ruler itself, must be equal to the moment anti-clockwise, which is the moment of the weight force on the apple. Okay, so the pivot is closer to the 50 centimeter mark than to the center of mass of the apple. Compare the weight of the rule to the weight of the apple. Okay, so the weight of the ruler is bigger because if it's got a smaller perpendicular distance, to make its moment the same, it must have a bigger force, so that the force times the distance come out as the same value for both of them. Okay. So a large stone block is to be part of a harbour wall. The block is supported beneath the surface of the sea by a cable from a crane. Figure 2.1 shows the block with its top face a distance h beneath the surface of the sea. The force acting downwards on the top face of the block due to the atmosphere and the depth is 3.5 times 10 to the 4. The top face of the block has an area of 0.25 meters squared. Calculate the pressure on the top face. We're just going to do pressure is force divided by area gives us the pressure in pascals or newtons per meter squared, exactly the same thing, so that's fine too. So atmospheric pressure is 1 times 10 to the 5. Calculate the pressure due to the depth of water. So we essentially need to take our previous answer, subtract 1 times 10 to the 5, and that gives us 4 times 10 to the 4 pascals there. Okay, so the density of seawater is 1020 kilograms per meter cubed. Calculate the depth h. So we can use the equation to calculate pressure at different depths. P equals rho GH. We rearrange to make h the subject. Plug in the pressure due to the depth of water, so we don't want atmospheric pressure in this equation. And we know what the density is. The gravitational field strength on Earth is 10, so we get it's a height of 3.9 meters there. Suggest 2 reasons why the tension force in the cable is not 3.5 times 10 to the 4 newtons. So the first reason I came up with is we've got an upthrust or a buoyancy force from the water on the block, which would decrease the required tension. And the other thing is the weight force on the block would increase the required tension, so that we haven't taken account of that force either. Okay, so the block is lowered so that it rests on the seabed. State what happens to the tension force in the cable. It becomes 0 because the normal contact force from the seabed and the upthrust will counter the object's weight force now. So you don't actually need any tension from your cable anymore. Okay, so we've got a diagram showing a dummy of mass 70 kilograms used to crash test to find out about the safety of a new car. All right, so the car approaches a solid barrier at 20 meters per second. It crashes into the barrier and stops suddenly. Calculate the momentum of the dummy immediately before the crash. Momentum is mass times velocity, so that gives us 1400 newton seconds or 1400 kilogram meters per second. Those two are the same unit. Determine the impulse that must be applied to the dummy to bring it to rest. So if it has momentum of 1400, the impulse must be minus 1400, so that its final momentum ends up being 0. Okay, so in the crash test, the passenger compartment comes to a rest in 0.20 seconds. Calculate the deceleration of the passenger compartment. So remember, acceleration is rate of change of velocity. So our change in velocity is minus 20. At the time is 0.2, giving us a acceleration of minus 100 meters per second squared, or a deceleration of 100 meters per second squared. The seatbelt and airbag bring the dummy to rest so that it does not hit the windscreen. The dummy has an average deceleration of 80 meters per second squared. Calculate the average resultant force applied to the dummy of mass 70 kilograms. Well, F equals ma, sometimes referred to as Newton's second law, is how we calculate resultant force using mass and acceleration. We know the mass, we know what the acceleration is, so the force must be minus 5,600. It's minus because it's acting against the motion of the, in this case, the dummy. Okay, the deceleration of the dummy is less than the deceleration of the passenger compartment. Explain why this is of benefit for the safety of a passenger. So, a smaller deceleration means the force on the passenger during a crash is decreased, and we can see that using F equals ma. And a smaller force is likely to lead to less serious injuries to anyone who's actually traveling in the car. So we would like to have a smaller force, and this is going to have happened because we're going to have increased the time over which they've stopped. That's what would give us a smaller deceleration. Okay, so now moving on to look at an extension load graph for a spring. Okay, Point P is the limit of proportionality. Name the law obeyed by the spring from the origin to P. That's Hooke's law. Hooke's law states that force and extension are directly proportional up to the limit of proportionality. Describe two features of the graph that show the law is obeyed. It's a straight line and it passes through the origin. Okay, so sketch a possible continuation of the graph when the spring is loaded beyond the limit of proportionality. So it's going to look like this. So once you go beyond the limit of proportionality, what you typically get is a lot more extension for the same force, which is why we see it curve up in that direction. So we get more extension for the same increase in load. Okay, moving on to part B of the general physics test. Define density. Density is the mass per unit volume, or mass divided by volume, anything that conveys that. The density of aluminium is 2.7 grams per centimetre cubed. The thickness of a rectangular sheet of aluminium foil varies, but is much less than 1 millimetre. A student wishes to find the average thickness, and she obtains the following measurements. So we've got the mass, we've got the length, and we've got the width. Calculate the student's value for the volume of the sheet. So to get volume, we're going to do mass divided by the density. We can plug those numbers in and we get our volume as 22 centimetre cubed. So now we can get the thickness, or the average thickness anyway, because we can do the volume. We're imagining it as a cuboid, so we're going to do the length times the width times the thickness to get the volume. So to get the thickness, we do volume divided by length and width, giving us 0.015 centimetres, or essentially quite a small fraction of a millimetre there. So another student provided with the means of cutting the sheet decides to find its average thickness using a single measuring instrument. Assume the surfaces of the sheet are perfectly smooth. Name a measuring instrument we'd use. We'd use a micrometer, or a micrometer screw gauge, to give it its full name. So describe the procedure she should follow to obtain an accurate value of the average thickness of the sheet. Details of how to read the instrument are not required. So first thing, micrometers are very prone to having zero errors, or having a non-zero reading when they're fully closed. So you need to make sure you don't have one of those, or account for it if you do. You would then want to measure more than one thickness. So what I would actually do is cut the sheet into pieces, stack them on top of each other, and we're going to measure the thickness of 10 pieces instead. We'll clamp the micrometer around the paper, so you use the ratchet to make sure it's touching but not squeezing the paper. And then you divide the thickness you get by 10 to get the thickness of one sheet. And I would actually do that. So I'm imagining we've got a stack of 10 sheets, so I'd actually pick a couple of locations to do the same measurements and calculate an average thickness overall. So the diagrams, we've got speed versus time graph for two different objects moving in a straight line. Describe the motion of the object shown in the graph 1. It's a straight line graph, so it's got constant acceleration, or it's constantly accelerating. Describe the motion of the object shown by graph in figure 1.2. That one, the acceleration is decreasing over time because the gradient is decreasing. On a day with no wind, a large object is dropped from a tall building. The object experiences air resistance during its fall to the ground. State and explain, in terms of forces acting, how the acceleration of the object varies during its fall. So the acceleration will initially be around 10 meters per second squared, because at very small speeds, air resistance is negligible, so its acceleration depends only on its weight force. So we get about 10 meters per second squared. And as speed increases, the force of air resistance increases because it's colliding with more air molecules per second. And that's going to mean the resultant force on the object decreases, which should cause its acceleration to decrease. Eventually you get to a speed where the number of collisions with air particles per second is sufficient that air resistance equals weight force. The resultant force becomes zero, and therefore the acceleration is zero. An electric train is initially at rest at a railway station. The motor causes a constant force of 360,000 newtons to act on the train, and the train begins to move. State the form of energy gained by the train as it begins to move. Well, it's starting to move, so it's going to gain kinetic energy. The train travels a distance of 4 kilometers along the straight horizontal track. Calculate the work done on the train during this part of the journey. Okay, so the work done is force times by the distance travelled in the direction of the force, giving us 1.4 times 10 to the 9 joules of work done. The mass is 450,000 kilograms. Calculate the maximum possible speed of the train at the end of the first 4 kilometers. So we're going to assume, if it's the maximum speed, that all the work we've done is to increase its kinetic energy. So we can then rearrange that to make the speed the subject, plug the numbers in, and we can see it's 80 meters per second for the maximum possible, but it's likely to be less than that due to work done by friction and work done by air resistance. In practice, the speed of the train is much less than the value calculated, to suggest one reason why that's the case. So that's what I was just discussing. We're going to have work done by drag and work done by friction, and they would both act to decrease the maximum kinetic energy by transferring some of the work done into thermal energy. After travelling 4 kilometers, the train reaches its maximum speed. It continues at this constant speed on the next section of track, where the track follows a curve which is part of a circle. State the direction of the resultant force on the train as it follows the curved path. It must be perpendicular to the train's velocity towards the centre of the circle. Those are the conditions required to be in circular motion. Okay, so the diagram shows a heavy ball of weight W suspended from a fixed beam by 2 ropes P and Q, each with a force of 30 newtons at an angle of 45 degrees. Okay, so the tensions are both 30. In the space below, draw a scale diagram to find the resultant of the tensions in P and Q using a scale of 1 centimeter to represent 5 newtons. Label the forces and show their directions. So we've got one force going diagonally up to the right. So we've got one force going diagonally up to the left. Both of those are 30 newtons, so they would each be 6 centimeter long lines, and we can see they produce a resultant force directly upwards, and we can measure its length, which I reckon is about 8.6 centimeters, giving us a force of 43 newtons. And we can see it's going vertically upwards, and we state its magnitude is 43 newtons. Okay, so on a day with no wind, a fountain in Switzerland propels 30,000 kilograms of water per minute to a height of 140 meters. Okay, so calculate the power used in raising the water. So I'm going to work out the amount of work done in a minute, and then we'll work out the amount of work done per second. That's going to be my approach. So in a minute, we have to do a total amount of work equal to the amount of GPE we're giving the water, because when it reaches its maximum height, its velocity is going to be 0, so it won't have any kinetic energy. So any work done will be to increase its GPE. So that's the work done every minute. But we want the work done every second. That's what power is. So we're going to divide that by 60 to give us the number of watts, or power, 7 times 10 to the 5. The efficiency of the pump is 70%. Calculate the power supplied. So what we need to do is essentially we're going to have to supply more power than the amount we've calculated, because we're only 70% efficient, and we divide by 0.7 to give us what that is. Okay, so on another day, a horizontal wind is blowing. The water does not rise vertically. Explain why the water still rises to a height of 140 meters. So what's going to happen? The reason we're saying it doesn't rise vertically is now going to go up at an angle because the wind is going to blow it sideways. But it will still attain a height of 140 meters because the wind, the force from the wind, acts perpendicular to the water's motion. So remember, the water is going straight upwards. The force from the wind, or the air particles colliding with the water, is acting horizontally. So it does no work in the vertical direction. So that means we must still achieve the same amount of GP, or the same final height, and that completes these sections of the test.